Okay, let's dive in. Today, we're looking at something a bit different. Not your usual research paper, but a collection of physics problems.
Right, almost like a workout for understanding the universe, wouldn't you say? These problems really push you.
Exactly. They're like little keys unlocking these huge, mind-bending questions cosmologists think about all the time.
And we're going to try and pull out some of the core ideas, the big takeaways you get from wrestling with this stuff.
So think about this first. You look up at night. What do you see?
Stars, right, like seemingly fixed, like forever.
Yeah, totally permanent. But almost the first thing these problems hit you with is that this picture is, well, wrong. The universe isn't static at all.
That's where Hubble's law comes in, a cornerstone concept here. It tells us everything's expanding. Galaxies are generally moving away from each other.
And the further they are, the faster they go.
Precisely.
Okay, so if it's all expanding, why do the constellations, the Big Dipper, Orion, why do they look the same night after night, year after year? It feels contradictory.
It really comes down to the sheer scale of things. The stars you see easily, they're mostly in our own galaxy, the Milky Way.
Our cosmic backyard, sort of.
Pretty much. And while those stars do move individually, what physicists call peculiar velocities, gravity holds our galaxy together pretty strongly.
Ah, so the local gravity effects overwhelm the expansion effect.
Exactly. On the scale within our galaxy, or even our local group of galaxies, gravity is the boss. The expansion of space is a much smaller effect there.
So you only really see the expansion clearly when you look much further out.
That's right. These problems show you need to look at truly vast intergalactic distances before that outward Hubble flow dominates over the individual peculiar motions of galaxies or the pole within a cluster.
So nearby stuff looks stable, distant stuff rushes away. It's a perspective thing,
A huge perspective thing. Different physics dominates at different scales. It's a key lesson.
which kind of leads us to another concept that feels, well, weird. Cosmic redshift.
Ah, yeah. The classic tool for measuring that expansion.
We usually think of redshift like the Doppler effect, right? Like an
Right.
ambulance siren changing pitch as it moves away.
Hmm.
Light waves from distant galaxies get stretched, shifting to the red end.
And that's the basic idea we use. But these problems, they make you dig deeper. They show it's not quite that simple.
How so? Like there's a problem here that asks about a galaxy that's technically at rest relative to the expanding space around it. You'd think zero motion means zero redshift, right?
You would, but in an expanding universe, that's not necessarily true. This is where you have to sort of let go of the simple ambulance analogy.
Okay.
The problems guide you to see cosmic redshift less as something moving through space and more as the light wave itself getting stretched out because the space it's traveling through is expanding underneath it.
Wait, the space itself stretches the light.
Yeah, over its long journey across the cosmos, it's a subtle but really fundamental difference.
Okay, that is mind-bending.
It really is, and the problems drive it home. They show, for instance, that if a galaxy has both a velocity from expansion and its own peculiar motion, the resulting redshifts don't just add up like simple speeds.
They don't.
No, they combine multiplicatively. It's a formula like 1 plus total redshift equals 1 plus expansion redshift times 1 plus peculiar redshift. It tells you something more complex than simple motion is happening.
Wow. Okay, so these problems are really designed to chip away at your everyday intuition about space and motion.
Definitely. And speaking of challenging intuition, let's talk about dark energy.
Right, the mystery component that's making the universe expand faster and faster.
Exactly. And the source material highlights its defining feature, negative pressure. That's the weird property driving the acceleration. It also breaks that old link between the universe's shape, its geometry, and its ultimate fate.
And this negative pressure, if it's strong enough, can lead to something pretty dramatic sounding, right? Something called the Big Rip.
That's the one. It's a pretty chilling scenario discussed in these problems. If the dark energy has a certain property, they call it phantom energy, where its density actually increases as space expands, which is extra weird.
Increases. How does that work?
We don't know how, but if it does, the math suggests the expansion rate doesn't just increase, it goes towards infinity in a finite amount of time.
Infinite expansion. What would that even do?
That's what one of the problems makes horrifyingly clear. It actually asks you to calculate the time until different things get torn apart by this runaway expansion.
Like what sort of things?
Everything. Galaxy clusters first, then galaxies like the Milky Way, then our solar system, the Earth, eventually even atoms themselves. The repulsive force of dark energy would overcome everything holding matter together.
Whoa. Ripped apart from the inside out,
Oh,
basically.
wow.
Okay, that's intense. Let's maybe shift from the end of the universe to the beginning.
Good idea. Because these problems also tackle a huge puzzle from the very early times related to the cosmic microwave background, the CMB.
The CMB, right? That's like the baby picture of the universe. The leftover heat from the Big Bang.
Essentially, yes. A snapshot from when the universe was only a few 100,000 years old. And the striking thing is, when we measure its temperature, it's incredibly, incredibly uniform all across the sky.
Which sounds good. Like, smooth is good.
It sounds good until you think about how it got so smooth. This is the horizon problem.
Horizon problem.
Yeah, if you look at 2 points on opposite sides of the sky in the CMB map, they have the same temperature. But when you calculate how far apart those regions actually were back when that light was emitted,
Uh-huh.
they were so far apart that there hadn't been enough time since the Big Bang for light or any information to travel between them. They were causally disconnected.
So how did they end up at the exact same temperature if they couldn't, like, talk to each other or exchange heat?
Precisely. It's like finding 2 cups of coffee miles apart that cooled to the exact same temperature at the exact same moment without any connection. It shouldn't happen in the standard Big Bang model.
Okay, that's a real puzzle.
Yeah, it is. And this is where theories like cosmic inflation come into play, which this material discusses. Inflation suggests there was a period of absolutely hyper-fast expansion almost instantaneously after the Big Bang.
Faster than light expansion.
The space itself expanded faster than light could travel across it. The idea is that it took a tiny, tiny patch of space that was small enough to be smooth and connected and blew it up exponentially fast to become the entire observable universe.
Ah, so it stretched out that initial smoothness across the whole sky we see today.
That's the core idea. It solves a horizon problem by making the universe we see originate from a single, tiny, causally connected region. These problems really make you grapple with visualizing that kind of event.
So going through these problems, we've gone from questioning why the stars look still, to space stretching light, to the universe maybe tearing itself apart, and now to how it got so smooth in the first place.
It's quite a journey, isn't it? And it really underscores how these aren't just abstract math exercises. They dig into the fundamental, often deeply weird nature of reality.
Yeah, they force you to confront how different the universe is on cosmic scales compared to our everyday world. The static view versus expansion, simple addition versus multiplicative redshift, the potential power of dark energy, the smoothness puzzle.
All emerging from just thinking through these structured questions. It shows how much our intuition, built for life on Earth, can be challenged by the cosmos.
Absolutely. It makes you wonder, if tackling these known problems already reveals such counterintuitive things about space, time, and energy, what other fundamental aspects of the universe are still out there, completely unexpected, maybe hidden in the next generation of questions physicists are starting to ask? What haven't we even thought to question yet?